Hi and welcome to this final week of Linear Algebra 2. This week is all about symmetric matrices. We will discuss diagonalization of these matrices and a wide range of applications such as optimizing quadratic equations in several variables and decomposing matrices based on their so-called singular values. Let's start with an example. What would you say is symmetric about this matrix? Indeed, it is symmetric with respect to the main diagonal in the sense that the entries above the main diagonal are equal to the corresponding entries below the main diagonal. Since taking the transpose of a matrix actually comes down to reflecting the matrix in the main diagonal, we can define symmetry of a matrix in terms of the transpose. Indeed, we call a matrix symmetric if it is equal to its own transpose. Since only square matrices have the same dimensions as their transpose, only these matrices can be symmetric. The definition of a symmetric matrix is therefore easy. So why are they useful? Let's first look at a practical application. Consider the following system of coupled masses and springs. The identical masses with mass m are connected to the wall and each other using springs with the same spring constant k. We measure the movement of the masses in terms of their displacements x1 and x2 with respect to the equilibrium position. Then, Newton's laws tell us that the displacements satisfy the following system of differential equations. Here, we do not focus on how you would derive or solve such a system. Instead, we rewrite these differential equations as a matrix vector product, and you see that the resulting matrix is in fact symmetric. In addition, several common linear transformations have symmetric standard matrices. For instance, if you consider a reflection in two-dimensional space about the line through the origin that makes an angle theta with respect to the x1 axis, you find that the resulting matrix is symmetric. Moreover, you might have encountered orthogonal projections previously, and one of the characteristic properties of the corresponding standard matrices is that they are symmetric. So the definition of a symmetric matrix is nice and easy, and they occur often both in practice and in linear algebra problems. So do they also have some special properties? In this video we will discuss two of these properties related to the eigenvectors and eigenvalues of symmetric matrices. The first theorem states that if A is a symmetric matrix with at least two different eigenvalues λ1 and λ2, then the corresponding eigenvectors v1 and v2 are orthogonal. The final theorem states that a symmetric matrix with real entries always has real eigenvalues, which is a very useful property of symmetric matrices. We postpone the proofs of these theorems to the end of the video. Instead, let's do an example first. Consider the reflection R through the subspace spanned by the vector 2 minus 1. Since this reflection leaves the vector u in its place, u is an eigenvector with eigenvalue 1. Moreover, any vector v orthogonal to u is mapped to minus v, so such a vector is an eigenvector with eigenvalue minus 1. So we see that this reflection only has real eigenvalues and that the corresponding eigenvectors are orthogonal. Let's turn to the proofs of our two main results. In order to prove the first theorem, we will show that the inner product of v1 and v2 is 0. We start by working out λ1 times this inner product. First, we use that v1 is an eigenvector of A with eigenvalue λ1. Then, we write the inner product as a matrix vector product. We work out this transpose where we use that A is symmetric. In the final step we use that v2 is an eigenvector of A with eigenvalue λ2 and rewrite the matrix vector product as an inner product again. We arrive at λ2 times the inner product of v1 and v2. Since these quantities are equal, their difference must be 0. On the other hand, as λ1 and λ2 are unequal, their difference can never be 0. This means that the inner product must be 0, which proves the theorem. For the proof of the second main theorem, we let λ be any, potentially complex, eigenvalue with eigenvector x. We aim to show that lambda times the inner product of x and the complex conjugate of x is equal to the complex conjugate of lambda times this same inner product. If we can then also show that this inner product is non-zero, we find that lambda is equal to its own complex conjugate and therefore a real number. First, we use that lambda is an eigenvalue of A with eigenvector x, and we write the inner product as a matrix vector product. Then, we work out this transpose and use that A is symmetric. Since A has real entries, it is its own complex conjugate. So we can use the additive and multiplicative properties of the complex conjugate to take A inside the complex conjugate. Then we can use again that x is an eigenvector of A with eigenvalue lambda and take out the scalar to arrive at the desired equality. Now, if we write x in terms of its components x1 up to xn, then we can work out the inner product and see that it is equal to the sum of the squares of the moduli of the components. This sum is bigger than 0 since the vector x is non-zero. Therefore, we can divide by this inner product, which shows that lambda is equal to its own complex conjugate. From this we can conclude that the eigenvalue lambda must be real, which finishes the proof. That's it for now. Make sure to practice these concepts and see you next time.